Okay. So indeed, I will tell you about interactions between convex geometry and entanglement in high dimensions. So I will try to use techniques from convex geometry to get some intuition on what entanglement looks like in large dimensions. So this is based on joint work with Staszek-Szarek from Cleveland. And probably the best source, if you want to look at this, is to look at a book which we just wrote, which is called Alice and Bob Meet Banach. So it's interaction between quantum information and Banach space theory. And it will appear this year, and there is a version on my web page. Okay, so I will consider the simplest case where we can discuss entanglement, so a bipartite system, and let's say CD tensor CD for concreteness, but D will be large. And then I look at states on this space. So a state, or for me, the same as density matrix, is something like this, a convex combination of pure states. So ρ is such a mixture. Maybe a basic remark is that for a given ρ, there are many ways to decompose it like this. It's highly non-unique, and this is really important. Okay, so now in this context, entanglement was, I think, defined by Reinhard Werner. So here the states, the pure states psi I, they live in this space CD tensor CD, unit vectors, and you ρ will be entangled if you cannot write it in this way with states which are product states. So ρ is entangled if it is not separable, where separable means of the form as here, but with product vectors. Of the form ρ is sum of lambda I psi I tensor phi I so now each of them lives in CD. And because of the high non-uniqueness of this decomposition, it's not easy to tell a priori if a given state is separable or not. Okay, so I will look at the states of all separable states and try to understand its geometry. So let me give a name to it. So sep D tensor D will be the set of all separable states on CD tensor CD. And so, as I said, it is a convex hull by definition, convex hull of all product vectors. So this set has really a large dimension. Dimension as a convex set. So they are operators on a space of a dimension d square. So it has dimension d to the 4, or -1 because of the trace 1 constraint. So even for the simplest case of 2 qubits, this set has dimension 15, which is, well, definitely much more than what we are used to look at with the usual world. But still, I will try to give you some intuition of what is the geometry of this set. So, okay, I will use a simple model to start with, because here, what you have inside the sphere of this space, you look only at the submanifold of all product vectors, and you take the convex hull of this. So here is an object which is maybe simpler and which has some similarities with this. And by the way, this week there are two international events in Paris. There is this conference and the Roland Garros tournament. So, okay, so why do I take this object? Because you see on this ball there is a line which is a submanifold, and taking the convex hull of this line is a bit the same as defining separable states, right? In this analogy, this line corresponds to product vectors, and what you get when you fill the convex hull are all the separable states. And I will keep this analogy in mind, and it will be useful at several places. So what I'm going to do is to define some invariants which come from convex geometry, to estimate them from this set, and to deduce from it some information about complexity of entanglement or typicality of entanglement. So I will try to draw some pictures. So maybe let's keep a pictures in a corner here. So this will be set of separable states. So there is a special point which is maximally mixed state, the most random state, which is identity over dimension, and entanglement lives out of this set, somewhere here. Okay, so so you see this set is a bit weird because it's not a polytope and it's not smooth either. It's when you take convex hull of this on this line on the tennis ball, you get some flat parts and some round parts, and the same is true for this set here. So it's a bit hybrid, not smooth, not completely discrete. But maybe a way to understand it is to try to approximate it by a completely discrete set. So let's try to approximate this set by a polytope, and maybe we will get some information. So approximation by polytopes. No question? Yeah? Well, for example, if you take in the diagonal basis, you will see a simplex, so a triangle. So it has corners in some sense. It's not a smooth manifold. It has some angles. Yeah. So yeah. Okay. So approximation by polytopes. So you can do this for any convex set. So if K is a convex set in Rn, you can try to approximate it by polytopes. So let's make a picture. So this is K. There is some origin here, and what you can do is you can look at K over 2 times smaller, and try to fit some polytope in between. So you can always do this. But now you can try to minimize the complexity of this polytope. And there are two ways to estimate complexity of a polytope. You can count the vertices, or you can count the facets, which are two dual ways. And these ways turned out to be very different. So to define some invariant, I will introduce the vertical dimension of K. This is, you take the polytope in between with the fewest vertices, and typically this will be exponentially large in n, so you take a logarithm to get something which behaves a bit like a dimension. So you take logarithm of the least number of vertices which you need to approximate K by a polytope. And now dually, you can count facets, so vertical and facial dimension. Now you count facets. So by facet, I mean face of codimension 1, given by the hyperplane. Now, these two numbers can be very different. For example, the cube, it has 2 to the n vertices, but only 2n facets. So typically, they can be, like this example, very, very different. OK, so can we estimate these quantities for our set? So if you look at the definition, the convex hull from this line, you can guess that there is a natural way to approximate it by a polytope with few vertices. You just discretize this line here, and you take the convex hull of the discretized set. And this gives a good estimation for the vertical dimension. So by simple discretization, we get a bound on the vertex dimension, which is of order d, and there is a log d term. So this set was a convex hull of a submanifold inside the sphere of this space of dimension which is about 2d, like the Segre manifold of all product vectors in CD tensor CD. So this is the reason for this d here. This is the dimension of the set of which we take the convex hull. But it's not clear at all how to obtain the dual estimate, how to produce a polytope with few facets. And there are deep reasons for which this is not easy. So this at this point is not clear. And actually there is an important result which is valid for all convex bodies, which I will now introduce. So maybe I will erase here. So for this I need two simple notions also. So again, k and 0 is here. So I will also need to consider what I call the in radius. So in radius of k here is the radius of the smallest ball center at the origin which fits inside k. And the out radius will be the opposite. You look at the smallest ball center at origin which contains k. So the ratio between these two radii gives you how far your set is from being a true ball. It's 1 if k is a ball centered at the origin. And now there is an important inequality due to Figel Lindenström-Millman, from the late 70s, which says it's a kind of uncertainty principle. It says that every set is complex in some way. So for every k convex body, convex body by I mean or convex compact with 0 in the interior of k, then the product of the vertex dimension, the facet dimension, and this ratio is large. Is greater than c times n squared for some constant c, which, well, as some numerical value. So this means that every convex set is complex, because in particular, among these three numbers, one of them has to be large. So either it's complex because you need many vertices to approximate it, or because you need many facets to approximate it, or because it's very far from being a ball. And in this spirit, the Euclidean ball is like the ideal of simplicity, as Plato may say. It's like the most perfect, the most simple object in this respect. So every set is complex. This is the moral of this inequality.
So for a sphere,
okay.
You would get.
I will. Yeah, I can illustrate this by examples, maybe. So sphere. So let's call this quantity A, B, C. So of course this is 1, yes. And now it's a simple fact to prove that any polytope which approximates the sphere has exponentially vertices. This is due to the fact that the spherical cup on the sphere has a very, very small measure in large dimensions. So this will be of order n. So this is sharp for the sphere. Now for the cube, it's sharp also. So the cube has many vertices, and even if you take something between two cubes of ratio 1/2, it will still have many vertices. This is small. There are few facets, and this is of order square root of n. The ratio for the cube between the in radius and the out radius is exactly square root of n. So again, it is sharp for this for the cube. For the regular simplex, so now it has a minimal number of vertices, n plus 1. So it's a log here. Same for facets. But now the ratio is n, so it's maximal. So for all these examples, this is sharp. And if we apply this inequality to our set of separable states, so you have to compute this quantity, which is not obvious. So the out radius is obvious because the states which are further from the yeah, this is 0, I should say. This plays the role of the center, this maximally mixed state. The further states are the pure states, which are product states. This is pretty clear. But what is the in radius is not obvious. It's a theorem due to Gurwitz and Barnum that it's the same as for the set of all states. So there is something to prove here. But if we take this for granted, you get a lower bound which is of order d cube. Okay. So maybe to make it more interesting, I will try to draw consequences from this estimate, which will illustrate the complexity of entanglement in large dimensions. So. Consequences about complexity of entanglement. So maybe I should say that there is a way. So if a state is entangled, it means that it is not in this convex set. Yes, this is entangled states. Now, you know from the Ann-Bernard theorem that if you are not inside a convex set, there is some hyperplane which separates from it. Based on this idea, people have come with a nice criterion to characterize entanglement. So this is the Orodeczki criterion. If a state rho is entangled, then there is a witness for it. Then there is a witness, namely, so by witness I mean a positive map. So if a state on CD tensor CD is entangled, there's a positive map phi from CD to CD, such that if you apply it to one copy of CD, what you obtain to rho is non-positive, such that identity tensor phi applied to rho is not positive semi-definite. So positive map means that it maps positive operators, I should say MD to MD matrices. So it maps positive operators to positive operators, but it's not completely positive. If phi is a CP map, then this always, by definition, is positive. So here I want to look at maps which are positive but not completely positive. So there is this fact that any entangled state can be detected in some way by this witness. And in some cases, this is even simpler. For example, if D equals 2, a single witness is enough, which is a transposition. So if you have a state on 2 qubits, and if you know its density matrix, and if you want to say if it is entangled or not, you can just apply transposition to one copy of CD, and if you obtain something which is positive as a matrix, the state will not be entangled. That's if and only if condition. But for D greater than 2, there is completely no analog of this, and it's a consequence of this this lower bound here. So I will write it like this. Even so, this even to approximate this set of separable states up to a factor of 2 requires a very large number of witnesses, exponentially many in this. So by this I mean that each time you have a witness, it cuts out some area of states which are guaranteed to be entangled. So each witness does something like this. But if you want to have something remaining which is up to a factor 2, the same as all separable states, you need really many witnesses. So there is really no analog of, even if you allow approximations or noise if you want, there is really no analog of this result in higher dimensions. And the reason for that is that we can count phase sets or count approximate phase sets. Each of these red curve brings that many phase sets, and since we know that you need many phase sets to approximate this set, you need many such red curves. This is basically the idea. So this shows that entanglement is complicated or rich in high dimensions, and maybe I can compare this to other statements. So people have proved, for example, that it is NP hard to detect entanglement, but in the following sense. Known, it is NP hard to decide between the fact for a state to be separable or to be outside a slightly larger homothetic factor of this set. So this is some polynomial in D. And this is proved by encoding some combinatorial problems which are known to be hard inside the boundary of this set. So the boundary is complex, and this is the reason for NP hardness. But here it's a bit different. We are only allowed to use a very weak model to test entanglement, which is only these witnesses. But for this model, we prove that the set of separable states is complicated from the bulk, because even for a factor of 2, complexity remains. So this shows in a different way that entanglement in high dimension is a complex set. Yes? So NP hardness, but if you want to, it's from computer science jargon. It means that if you want with a Turing machine to decide between this alternative, it's as hard as the classical, well-known to be hard problems in computer science. So it means hard. Just, but yeah. Because we don't know if P equal of NP or not, you have to put these cautions, basically. But it means hard, known to be hard. Okay, other questions maybe at this point, because I will move to a different topic now. Okay, so, yeah.
You said that the boundary of the set is complicated, but can you scale the meaningful in terms of whether to extract some fractal dimension of the scale? So if there is many faces in one direction,
they are not exact faces. So in this argument, it's like counting approximate faces, because it's always up to a factor of 2. So I don't think you can say something like this. Yeah.
Yes, do you think that it is a semi-algebraic set defined by inequality with polynomials? Is it something like this or not? Because it has an interior.
Yes.
The interior is not empty, it contains identity.
Yes. Is it semi-algebraic set? So for D equal to yes, because of this, but it's very specific. I don't know. Yes, it's not clear. Not to me. But yeah, yeah, it looks like a natural question. So, but I don't know. There is no obvious reason why, if I can tell. But okay. Yeah. Okay. Other questions? Okay. So another way to estimate the size of a set, so I will not try to have another look at this set by trying to see how large it is in some sense. So how large is this set? So again, I will make a picture. So now start with a unique convex set K in Rn again. So take a unique vector U. And then you can look at the width of K in this direction. So I look at the hyperplane, which is as far as possible touching K in the direction U. And this length here, I call the width of K in direction U, or WKU. Now, this quantifies how large is K, but typically this will be hard to compute for more or less the same reasons as here. So this will be not easy to compute even for a given U. And also another way to measure how large is K is this length, which is shorter. And this I will call 1 over J, Jk of U. The reason for this is that if K is a unit ball, this will be the norm for which it is a unit ball. So if K is symmetric with respect to the origin, then it is some unit ball for some norm, and the norm can be retrieved by looking at this length here. And actually, there is a duality between these two notions. We can define a dual set K star in such a way that these two quantities are switched. So in such a way that the width of K is the gauge, so we call this the gauge of K star. And again, if K is the unit ball for some norm, this will be the dual norm, which is just duality for norms at the level of unit balls, and also without the symmetry constraint. And again, these quantities are hard to estimate for a given U. But what you can try is to estimate the typical value. Now, if you take a random U, maybe it's easier to estimate the typical value than a given value. So you can look at the mean width or the mean gauge. So if these are hard to estimate, maybe consider the average. So the mean width W of K is the average over all directions from the sphere with the invariant measure, invariant probability measure. So average of this mean width with respect for U uniform on the sphere. And also there is so as I said, the green length is shorter than the red length. So this means that the product of WK and GK in every direction is greater than 1. So it's obvious from the picture that WK times GK is greater than 1, or this also I can write as the width of the dual set. And now if you have such a pointwise inequalities, it remains true after integration. So also the mean values will also satisfy the same inequalities. Mean width of K times mean width of K dual is also greater than 1. And okay, now it's if you have a set which is very thin and very long, well, it's clear that in a typical direction, the width will be much longer than this length. Yes, but again, it's a deep theorem from Banach space theory, which tells you that you can always rebalance your set to make this product small. So theorem. So again, Figiel, Tomczak, Jagerman, and Pizier, again from the late 80s, tells you that if K is convex, and now I assume that K is equal to minus K, so that K is symmetric with respect to the origin. We don't know if it holds without this assumption. So it's not true that this product is small because of this long, thin body, but always you can find a linear map, GL and R, such that if you apply it to K, so you get a new convex body L, and this new convex body satisfies this. This quantity is bounded. Satisfies mean width of L star, which is, well, bounded by log n. So you can rebalance K in such a way that the typical width is only log n times larger than the typical length in the picture over there. And this is a deep fact from Banach space theory. And again, I will apply it to my set SEP and see what it means. So how to compute this averages for SEP? So again, the width in a direction will be achieved on an extreme point, so on the line here. And so you can believe that it will be easier to estimate the average width than the average length, because what the lengths look like, you have to understand how the facets are, and it's messy. So again, by a standard discretization argument, you get that the width, you estimate the width of this set, so which is of order 1 over, well, the value is not important, just we know, I will explain later a reformulation of this. And now, okay, I claim that you can apply this result. We can take L equals this set, which is not clear because first it's not symmetric. The set of states is in a direction of a pure state is much longer than in the opposite direction. And even this part is not clear why you can take T equals identity, but in this case it is true. To conclude that the width of the dual set is known up to a log factor. Okay, so this is not very transparent. So let me give an illustration. How much time do I have? Okay. So illustration for entanglement of random states. So take a state, a random state on CD tensor CD. So how do you define such an object? So there are many ways, but one way which is maybe more canonical, you know that every state can be purified if you use some ancilla. You can look at it as a partial trace of a pure state. So you can use this idea. You start from psi, a pure state in your system tensor some ancilla, so Cs for some s integer, and now psi, it's a vector on the unit sphere. There is no a way to take it randomly, just take the uniform measure. So take psi according to, so randomly, uniformly on the unit sphere. And now take rho the partial trace. So you forget the ancilla. And this way you obtain a pure state, a mixed state on CD tensor CD. And you can ask what happens when S varies. So let's look first at limit cases. If S equal 1, so there is no ancilla, so you just take a pure state on CD tensor CD. So clearly it will almost always be entangled, because it's like you hit a random point on the ball, and unless you hit exactly the line, it will be outside the convex hull. So with probability 1, a pure state is entangled. Then rho is pure and entangled with probability 1. And now if S tends to infinity, so what happens when the ancilla becomes very, very large, then I claim that, again, almost surely, rho converges to the maximally mixed state, to the center of the set. So this amounts to the law of large numbers, or maybe you can invoke decoherence to explain this fact. So when S becomes larger, the effects become so important that everything collapses to the maximally mixed state. So rho converges to identity over d square, which is not entangled. So we expect some transition between these two regimes, a critical value of S at which entanglement becomes typical. And this value is exactly related to this parameter. So theorem.
What do you expect the transition of another crossover?
Okay, I don't know what is the difference.
It was abrupt for a precise value of S.
Ah.
It happens over a certain range.
Okay, okay. I will discuss. I will. Okay, we expect a change of behavior. So, theorem. So define the critical value in some sense as 0, depending of d, as the square of this quantity. So it's of order d cube. So then this is the critical value, or whatever you call it, in the sense that for every epsilon, if you are slightly below this level, then the state will be entangled with large probability. Let's say with proba tending to 1. And if you have above, the state is separable, non-entangled, again with probability tending to 1. With D, yeah. As D tends to infinity. Yeah, so it's always large dimensions.
So in fact, the transition is sharp when D is infinite, somehow.
Yes.
There is a square in the definition of
Square, yes. Square, thanks. Yes. So, okay, and maybe I can again give another formulation which is even maybe more appealing. So, reformulation. So now let's count dimensions by using powers of 2. So let's say that you have like n qubits in a global random uniform state, pure. So this means that you take in the sphere CD to the n, you take a randomly unit vector. And now what you do, so you have n qubits and particles, and you split them into 3 groups. You give k of them to Alice. You give k of them to Bob, and the remaining you give to the environment. And the question is, when do Alice and Bob share entanglement after you trace out on this part? And if you reformulate this into this framework, what you get is there is a critical number of particles, and it will be even sharper in this sense. Then there is a critical value Kn, which is of order n over 5, such that if you give more than this number to Alice and Bob, then they will share some entanglement. So again, with probability which tends to 1 as n tends to infinity. And if k is less than kn, they do not. So the transition is sharp in the sense that even if you move by 1 and if you go above the threshold, then the typical behavior changes dramatically. Yes?
So since the environment is typically very big, we essentially never see entanglement.
Yes, so you can, but of course this is the problem of this model is this is not realistic at all. But yeah, in some sense this explains this. Yeah, right. Okay, so yeah, so maybe the next step will be to replace this model by a one which is more realistic and still tractable to these methods. And this I don't know of any candidate. MPS? Yeah, maybe. So, okay, I will stop here.
Okay, thank you.
Okay, so but this is very finite dimensional. I mean,
I mean, if you think of the quantum field theory or so, then you're forced to look at Riemann algebra.
yes.
With
So
freedom and so on.
in Banach space, it has been very fruitful to approximate infinite dimension by large finite dimensions. So maybe you can do the same here, because this makes typically no sense in infinite dimension, like harmonic on the sphere. What else was typically like counting facets or polytopes. But what you can try to do is to approximate by large subspaces or subalgebras and see how parameters behave, and maybe you can get some information here. But basically everything is finite dimensional to start with. So yeah.
I would like to make a point a bit back to physics. As you know, say, in quantum mechanics, since it started about 100 years ago, physicists have always tried to look for limits. And they consider, say, collective variables built out of many individual degrees of freedom. So you can wonder, is, say, the gravity center of a big object, is it a quantum variable? And all the answers of questions of this type have answered positively. So many particles that build single degree of freedom, this single degree of freedom behaves quantum mechanically as far as investigation could be performed. But there is, I think, a much more interesting direction, which is the one that we have discussed, which is the size of entanglement. So rather than asking if a heavy object can be quantum, the question would be, can, say, they do really high dimension, large entanglement objects, can even they exist? And as you pointed out, these entangled states are very difficult in some sense. So even calculating the evolution of a complex entangled state is very hard task for the physicist, and you can wonder if it's not also an equally hard task for nature. So the question could be, is there some limit on the size of entanglement that can be achieved in the lab or on nature? And I wonder if you thought about establish some relation with what you
Not really, but something I can say is that, so here it was like a yes-no world, so it's very binary what I presented. But then you can try to quantify, because entangled states, they are not all similar. They are more or less entangled, they are more or less useful. So yeah. So when you go into this, it becomes less clear how to use these techniques. But no, I don't really know of any limitations. So I try to apply these mathematical theorems to this situation, but I
or flat irons, physicists are now able to address, say, high-dimensional entangled states. So maybe you could discuss with
okay.
So, of course, the idea of entanglement is a sort of very old idea going back to Schrödinger and so on. And I very much enjoyed this talk, but what I never really understand is what does it make it so fashionable at the moment? But how can you use all these things in practice?
because of quantum information.
Yeah, quantum. That's what. Okay.
I think that your quantum computer stops working at 64 qubits. On bad shape. Anyway, it doesn't work at 2 or 3.
No, I think that's the yeah, I agree with this.
There is a limit to entanglement in some sense. It means that the quantum computer would never work on the large scale.
I don't know what you want to compute with your quantum computer.
You want a factorized number.
So you count the number of faces when that you can put between K and K over 2, but you can ask the same question with a different sketch factor.
Yeah, it changes nothing. If you replace 2 by another number, only the constants change.
Even when the sketch factor goes to 1?
Yes, it behaves very nicely with.
If the boundary is very irregular,
But
number of faces
it explodes, but like, typically in log of the approximation ratio. So even if you want, like say, to a factor not 2 but 1 plus 1 over d, that's fine.
it's not a way to be physical with the structure of the boundary.
No, you. No.
How is the dual set larger than the initial one? Can you say?
Yeah, so let's start for states. So if D is states on CD, then the dual set is D times larger. So this means in this formula you have to interpret this point as the 0. So the same will be here. It will be like D squared times larger somehow. But it makes no sense to compare because if you change the scaling, then it shrinks. I mean, you can if D is larger, D star is smaller. So yeah.
Okay, more questions? Antoine.
Perhaps a more general question. The analysis is made mathematically very difficult and so I guess also interesting by the definition we take of entangled states. Basic. It seems that it's not so, for physicists, is this definition operationally relevant, like does it correspond to natural thing? Because it seems that if in an experiment I can easily see if a state is entangled, it means I can easily characterize it and so.
But how do you see it? Correct.
I have many copies, I do many measurements. Is there a way to see it? To see that they have an entangled state or some sort of operational characterization of entanglement in that sense?
Well, I don't know, and I will be. I will let experts. So.
Is there a way to define another measure of entanglement or other understanding of what it means to be entangled that makes things easier?
So there are many measures, but
Or separate?
yeah. So you can say that you can say that if they violate some Bell inequalities, then they are entangled, for example. But then it's not always clear if all the definitions coincide, and you get to some problems. And anyway, if you want to apply convex geometry, then definitely this one is a natural one.
Okay, so merci, thank you.